Alright, so my name is Loni and like Ka just said, I'm just beginning. So I joined Andy's lab about a year ago, and I started actually taking over the 2DFS system and running my own experiments in January. It was actually the week Sonori was visiting that we did the transfer as Julia, the grad student before me, went on to her postdoc in Michigan. And so today I'm going to tell you about some of the experiments I've done in the past couple of months looking at the ultrafast dynamics of zinc tetraphenylporphyrin dimers using two-dimensional fluorescence spectroscopy. So why would we want to look at these systems? Well, a lot of groups have been studying like the large photosynthetic compounds, but we wanted to be able to better understand what's going on within the membrane protein system, and so we wanted to start with a smaller model system before we try and understand these large complex systems. And so by putting porphyrin inside of a liposome structure, we can understand how this liposome is trapping the molecule and confining its conformation. So the only way that it can change conformations is if the hydrogen bonds with the liposome break, and this allows the porphyrin to change how it's oriented. And so we can also learn about the solvent itself by looking at the liposome and how its spectral diffusion is changed when we look at the molecule in, say, like chloroform or some other sort of solvent. So the technique we use is phase-modulated two-dimensional fluorescence spectroscopy. And so this is a picture of the laser setup that Wombe took. So what happens is we have 4 collinear pulses that excite our sample, and we detect the fluorescence. So in a given scan, we're scanning the time delay between pulses 1 and 2 and between pulses 3 and 4 at a set population time, or capital T. So this is the schematic of our laser, and so we have our TISAF laser pumping 2 OPAs. We are using 250 kilohertz pulse repetition rate, which is different from the setup that is here. And then we send it into 2 Mach interferometers, and we control the modulation phase difference between our pulses using acousto-optic Bragg cells, which are these gray things here. In some of our experiments, we also want to look in the UV. So like say if we were going to look at the 6-amine molecules that Wombe discussed, we could put in second harmonic generation apparatus in there, and so we could go into the UV instead of just being limited to the visible range. We then control the delays and detect the fluorescence, and we use lock-in amplification. So we pick off from our incoming beams a reference signal, and so we are modulating at 5 kilohertz and 8 kilohertz, and so we pick off those frequencies, and then using an electronic mixer we get out the 3 and the 13, so the sum and the difference, to be able to look at our fluorescence action signal at this nonlinear interaction. So when we collect data, it looks like this. So you have your non-rephasing signal, which is your sum, as well as your rephasing signal, which would be the difference. You can add these two together to get your total correlation spectra. And then you get a real and imaginary component, where the real would be like the cosine portion of your oscillating term, and the imaginary would be the sine portion. And so when we want to interpret our data, we often use a simple 2-level dimer system. So if we look at our dimer as Frankel excitons, we have in our monomer state we have a ground excited state and then we have a ground state and an electronically excited state for both of our monomers. But then as a dimer, where they are close enough together that they're interacting, and so they interact as in concert with each other, so the excitation can be delocalized across the two. You get your ground state, 2 singly excited state, and then your doubly excited states. So then when we look at our spectra, so this would be like a model of a 2D total correlation spectra. You would have a dot along the diagonal that would be your lower energy state, so the minus ket, as well as your higher energy state, or the plus ket. And so if you were to just look along the diagonal line, that would be equivalent to like a one-dimensional fluorescence technique. But the advantage of using two-dimensional is you get these cross peaks that indicate the coupling either from the higher to the lower energy or from the lower to the higher energy. And we can look at how these different peaks change in shape and intensity as a function of the population time, capital T, to learn about how population transfer is occurring in our system. So each of the peaks is, their intensities are governed by these different terms. So there's a ground state bleach term, a stimulated emission term, and excited state absorption. So in each of the four cases, there is a stationary or static ground state bleach term, because during that delay between pulses 2 and 3, you're in the ground state, and so you wouldn't have any population transfer. But then Green's function, which is a solution to the quantum master equation, can be used to determine the probability that that your excitation is going to transfer from one state to the other, or stay in the same state. And so this can be applied for this stimulated emission and the excited state absorption terms. One of our differences with 2DFS versus like two-dimensional photon echo is this gamma term. This is because in our technique we're looking at the fluorescence, so we're looking at an action signal from this nonlinear process. And so the excited state absorption, there are two different pathways that lead to this. One is from the doubly excited state and the other is from the singly excited state. And so the molecules in the doubly excited state, some of them are quenched, so not all of them are fluorescing, and this gamma takes into account that. So if we have all of our doubly excited molecules fluorescing, gamma would equal 2. If none of them fluoresced, gamma would equal 0. And
how do you know which gamma to put? How can you measure it independently, quantum U from W?
So we use a modeling system. It's one of the parameters we have in when we model our data using computer analysis.
Can't you just measure it?
In principle, you can like what?
No, it's probably impossible.
No, it's possible. You can look at like if you're talking about, they say quantum dots or things like this, then it's basically something related to the lifetime of the doubly pi excitons to the lifetime of a single exciton, something like this. But here, as I don't think it is exactly possible to that, and they just use it as a fitting parameter.
Can I just ask, why is it different? Why is the two exciton state quenched?
So they can annihilate each other.
Oh, okay. So it's, yeah.
Okay, so this is just okay. So it is not a double excited state. It's two excitons.
Yeah. So there's two excitations within your dimer.
Okay. So this is kind of fun. But then it should have intensity dependence, like excitation intensity dependence. It's kind of clear.
Yes.
That's a dual pathway, so it is there no matter what you do. Your whole thing is for wave mixing. So it's intensity dependence is not part of the equation here. So you do end up having 4 interactions anytime. Doesn't matter what is your intensity. But you are right, it's annihilation-related type of things. But it is also, it can happen in the monomer too. It doesn't need to be 2 excitations at your 2 different.
So that's just basically Kasha's rule. If you have a double excitation in the same molecule,
That's right.
it should be identical.
Yes, if it's coupling to the environment, whatever, if it's fluorescence quantum yield is same as the singly excited state, it would be 2. That is,
Yeah.
but usually you don't have that.
No, if you have singlet annihilation, then it's of course. Yeah.
So using our probabilities, we can kind of approximate what our signal will look like in different scenarios. So for example, if we had the case where we were only transferring energy downhill instead of uphill, we would see a decrease in the intensity of the upper off diagonal and an increase in intensity of the lower upper diagonal and the lower off diagonal. So the system I'm working with is two zinc tetraphenylporphyrin molecules that are linked together with this covalent linkage. And in previous work done by Julia, she looked at these molecules in a temperature-dependent study to examine the different conformations they can take. And she found that there were two states, the extended form and the folded form, and these occurred in a mixture within our system in the DSPC, or our liposome structure. And so when...
Can I ask?
Mhm.
What is this gray level?
So the gray level is where we're fluorescing from, so there's some vibrational relaxation from the absorption before it fluoresces. So I took these molecules, placed them into the DSPC liposome, and when I prepare the samples, I anneal them to 70 degrees Celsius to begin with, and then cool them down to 17 degrees Celsius. This is to raise the temperature of our liposome structure, so beyond the liquid crystal phase, and so it can reorient itself. And then we took population time. So the population time is listed in the bottom right-hand corner of each plot. This is plotting the total correlation functions of our system. And so this would be our lower diagonal peak, our upper diagonal peak. Around here is our lower off diagonal, and up here is our upper off diagonal peak.
What is the kind of resolution in this experiment? We have this blob. Can you measure instrumental response function with any sample that could allow you to see what is the minimum feature you can resolve in your plot?
I'm not sure, because we have so much spectral diffusion going out into our system, and just the vibration modes, the different energy levels.
If you just take a dye molecule without any extra, just one like kind of a solution of dyes, can this be used as some kind of response function measurements? Because now I kind of understood my kind of a feeling about all these 2Ds. So I mean, well, I can see the picture, I can see the spots, but I never know how small spot can be if you would just have only one transition. You know, what is the limit because of your technique, or what is really kind of weights you have from the molecules, from this whatever homogeneous broadening or diffusion or whatever.
I'm
Can
not
one ever?
sure.
But it's more like
I
a
would
general
think
question to
at
all
these
people.
temperatures, it's really the absorption spectra are so broad. It's I don't think it's the technique what limits here the resolution. Your inherent absorption spectrum, or whatever you are measuring, is so broad. I think that's the...
Because it's not only spectral resolution, it's also kind of resolution in time, because if
Yes.
you compare
That's
pictures,
fine.
then one need to, it's all convoluted in one thing. So it's,
In principle, I mean, one can get better resolution. For sure, it's just about how long you measure. So in your case, I guess you're measuring up to, what is the...
So we were going in 10 femtosecond steps up through 200 femtoseconds.
That gives the sort of resolution you can have, but there's also a bit of the thing that, yeah, you're right, there's also, because we don't just use this data, we have to do windowing and other things that kills the resolution a bit.
for example, if I see this kind of shape which look like a skull, I don't know, by some reason, like this, is it really the skull, or is it just an error, you know, if in some of the procedures, and it should be like a round, or this skull?
No, here I think it's a skull.
So it is real.
Yeah, it's real. Well, the resolution here is better than what you were saying. Because 200 femtoseconds, well, you should be able to resolve maybe 15, 20 inverse centimeter or so.
Yes, but of course it also depends on that the detective kind of noise you have, because what we
Oh,
measure
okay.
here is the signal, and maybe So it's all together, it is what I mean. It's
Yes,
all
yeah, the
contributing.
noise in this case, what was the locking time constant, I guess?
So 300
milliseconds.
milliseconds.
That's like 3 hertz bandwidth of the
Mhm.
thing. So the noise is eliminated, at least from that point of view, quite a bit. But there's also, yeah. So
Just what I want to comment, when you measure absorption spectrum, it's already quite difficult to say, okay, what is my accuracy in my absorption spectrum, but this is so complicated.
Yeah.
Comparison to that, so, but people usually don't talk about it.
Well, as the field develops.
Hopefully, yes.
Yeah.
So did you say you scanned this coherence delay for 200 femtosecond with 10 femtosecond step?
Mhm.
So it's only 20 points
Yeah.
in your 1,000
It's
in your x
200
direction.
steps, yeah. Or
200
two- 20 steps. 20 steps
20
across.
steps on 1 point
And then 20 steps up.
1200 inverse centimeters plus windowing. So
So from this data, we could see that as we increased our population time, our upper off-diagonal peak increased from where it started, as well as our lower off-diagonal peak was increasing. This indicated to us that we're having uphill population transfer rather than downhill population transfer. But I'm still working on the data analysis to confirm this. This is fairly new data. But we could also place points on our spectra, so picking specific spots along the diagonal and then the off-diagonal to get a better estimate of the time it's taking for this population transfer to occur. So instead of trying to do it by eye. So in this case, I normalized the spectra to a point near the upper off-diagonal. And so we can see that our lower diagonal peak has a population time transfer. So this is fitting like an exponential to our curve. So our time constant is about 65 femtoseconds for our lower diagonal peak, and for our upper off-diagonal peak, we're at about 98 femtoseconds. So our population transfer between our states is occurring around that time scale. And then beyond that, it is in a more stable, or it's past its transfer time. Yeah.
Just one quick question. What you call your lower diagonal peak, below that you have, let's say, like in your school, where you have state that.
Yeah.
Any idea what that state is? Is it?
I'm not sure what that state is. We speculate it's possibly a dark state that's occurring that we wouldn't see in like a normal spectra, but is appearing in this case, but we haven't had a chance to analyze it yet.
And okay, now I got this. So all the signal is the fluorescence, right?
Mm-hmm.
Here, this is signal I can understand, not like in you.
Where is it? Where is it?
No, but you too, yeah, exactly.
But I think the information is the same, by the way.
Yeah, exactly. But it is a signal. I understand what it is.
But those points what you have singled out, these are where you expect to be those exciton levels and the cross peaks. Yeah.
Yeah.
Well, why do you say that you see uphill transfer? From those curves, I would still say that from blue it goes down to.
So I'm saying it's uphill because there's a larger change in the uphill transfer because we're in a mixture of states. Both are occurring, but it's favoring the uphill transfer.
But the blue
Yeah.
diagonal goes down,
Yes.
and the corresponding green cross diagonal goes up.
Mm-hmm.
That means that you relax down.
Yes. So
And what do you mean by uphill
so
transfer?
because so it's in the mixture of states. So there's some that are in the extended form, some that are in the folded form. So the ones that are going from or transferring energy from the extended to the folded are it's favoring that transition, but it's not limiting out the case where it's also doing downhill. So both are occurring at the same time, but these two peaks are being governed by the downhill transition. These two peaks are being governed by the uphill transition. So you'll see the extent of both of them at the same time, but we, because there's a greater change in these ones, it's favoring those.
Does it make sense just energetically to have uphill transfer areas, 200 wave number difference between these two states? I don't know what KBT is at 17 degrees. Does it make sense?
Yeah, well, it's a bit more than QT, close.
But should you go faster up than down, which is happening here?
It's usually down, yeah.
I'm not sure. We're still working on that as well.
But I mean, it should kind of equilibrate in principle, right? So it can go
Yeah,
both
but
up
this
and
is-
down, but the
This is not what you see. You see the
Yeah.
upper cross peak is increasing in intensity faster than the lower one does. It means that you excite the lower state, and in average it moves up.
On the other hand, if you would excite just one state which is very low, but you have states up and this is KT, it will move up in average. If you start here,
Yeah,
and then you have states there and KT is like this, then in time it will move up.
but in this case, let's assume that your spectrum is completely flat. You excite everything equally, and basically what
Then
you,
it should go down.
yeah, and basically what you see here is that it goes up.
Yeah, but then it's
Just one small comment, I don't know if that's relevant or not, but you say that you have a sort of H configuration and a J configuration, and you're measuring fluorescence.
Yeah.
But the H is in principle very less fluorescent than the J.
Yeah. So we place our laser spectra, so we're favoring the excitation of that one much more than the.
You excite more the H than the J.
Yeah.
And then at the end you think that you expect similar fluorescence from both, or?
So we are. We know we're not seeing like equivalent amounts of both, but we just wanted to be able to see fluorescence from both.
So why do you want to see them both? It's a complicated picture. Can you just make one sample with only J and the others? Why is it impossible?
So we can use filters to filter out the fluorescence. We can, because we know approximately based on one-dimensional where those two are separated. So we can place filters there so we can study one at a time. But in this case, we wanted to look at both at the same time to be able to study the transfer from one to the other.
But transfer from one, do you mean that you have in one liposome or whatever it is, two types, J and G and H, or do you, because you showed that picture that you have a liposome,
Yes.
and then you have something in the middle, and I thought in the middle you have just one molecule basically, but you have many.
We don't actually know exactly what it looks like
Uh-huh.
inside our liposome. We can't measure that. So we can kind of speculate based on the spectra that we are given that there is transfer going on. So I would suspect that there are more than one, but we don't know for sure. And so the population transfer isn't the only thing that affects our 2D spectra. We also have changes due to the spectral diffusion. So in the case of like very short t equals 0 population times, we would expect it to be elongated along the diagonal because of inhomogeneous broadening. So the fact that each molecule is in a slightly different environment allows it to absorb and fluoresce at slightly different energies. But then as we increase our population time and we go into the homogeneous broadening, we expect it to elongate along the anti-diagonal, and so we can get an estimate of the time at which this dephasing is occurring by taking slices along the diagonal and along the anti-diagonal, fitting those to a Gaussian, and then finding the full width half max of this, and plotting the anti-diagonal versus or anti-diagonal over the diagonal to get this time constant. And so in this case, we did this using our rephasing spectra. And so our slices along our diagonal are plotted here. And so the lighter blue is occurring at shorter population times, going to the dark black, darker blue, which is our long population times. And then the green is when when I return to 0 at the end of the day. With our diagonal peak, we couldn't fit a simple Gaussian to it. We had to use, I had to use 2 Gaussians and then convolute them together. And so then when we plot this, we see that for our dimer in the liposome sample, we were getting a time constant of about 85 femtoseconds, which is very similar to our population transfer time, which was interesting. I'm not sure why we expected it to be shorter. But we also looked at our dimer in chloroform, which is this red curve, and we didn't see any dephasing time constant where that's because it would be occurring faster than we can measure it. We also looked at the monomer, so just a zinc tetraphenylporphyrin in the liposome, which is the blue, and then the monomer in chloroform, which is the green. One interesting thing we saw is that there wasn't much of dephasing in our monomer in the liposome. We expected there to be because this was a measurement of kind of the environment of our solution, and we expected in similar solutions that it would have at least measurable time constants. One of the possible explanations for this is exchange narrowing. So in the dimer situation, you have more states over which our excitation can be occurring, and the stronger coupling allows it to have a longer lived lifetime versus our monomer where it's more confined and will more quickly diffuse, and the nuclear motions will diffuse with our electronic motions. That's just a speculation at this point.
What is the size of this hole in the liposome? What is happening? What is the, or, I mean, so all this DSPC is this thing, right?
Yeah.
So what is the size of that, of that vessel in the middle where the molecules are? Is it like 100 nanometers or 10 nanometers? Or
I think it's on the order of like tens of nanometers, but I'm not sure. We follow the standard procedure.
because then if you have a, if you have just a monomer there, it's still quite big for it, but if you have a dimer, then it's not enough to really move forward. In the way it wants to. That's why maybe you have this slow changing.
Yep.
It's basically like kind of in a solid state, but not
Yeah.
really because it has
I will look into that. That is an excellent point. I'm not sure at this moment. And then, so like I said, I'm rather new at this, and quite by accident, I discovered that if you leave your samples in the refrigerator for 7 weeks and then collect data on them, you get a much different structure. So these are the samples that if you prepare them just 5 days before, you get this sort of shape. So it was the mixture of the extended and the folded conformations. But if you let it sit in the refrigerator, they form pretty much all are in the folded state. And so we're not sure if this is a more stable configuration or if it's because the liposome sitting in a refrigerator has different properties. And so this was quite interesting and really exciting for.
I just want to make a comment in all this kind of self-assembly. The tiny change of the condition makes a very big difference. For example, when I was doing my PhD, I was having a very good samples for a while, and then it actually stopped working, and that's because I used different water. It was still water, but it was from 2 different bottles. And nobody knows what was it. One bottle it worked, and the other it never. So then it's very.
Yeah.
I'm not surprised at all.
I guess you should also cross your fingers and hope that it's not necessary for your project to have 7 weeks of preparation time.
Yeah, I hope so as well. Because it was frustrating. But with this case, we did see that it was favoring the downhill transfer. So we're seeing the decrease in our upper diagonal and an increase in our lower diagonal. So that was exciting to see. And then when we looked at the dephasing, it had a much shorter time constant, about 20 femtoseconds.
But can it be a size of these liposomes?
I'm thinking probably, yeah. So I'm currently working through all of this data, trying to model it, and trying to understand what's going on. But in brief, our conclusions are that we can at least examine energy transfer in these porphyrin systems that are linked dimer mixtures favor uphill transfer and a slower dephasing constant than our folded conformations that were exhibiting the downhill transfer. In the future, I will start working on the DNA systems that Wambe talked about, using 2DFS to study the conformations that these base pair analogs take in the presence of various proteins and looking how those change. I would like to thank my group, so Andy, my advisor, and Pete are my co-advisor, and then especially Julia Whittam. She is the grad student that taught me 2DFS before she left for a postdoc in Michigan. She left in January. And the rest of our group, Mari does a lot of my one-dimensional spectra, and so she's an undergraduate in our lab and is very helpful on that. Are there any other questions?
Again. You have some very, very short time constants you measure here. So you're talking about processes with 20 femtosecond and these kind of things. How confident are you in these time constants?
Our pulse duration is about 30 femtoseconds. So with these really short ones, I'm not incredibly
So you're basically completely in your pulse overlap.
With our short ones, yes. With our slower, the 85 femtosecond one, we're more confident with that than our 20 femto.
Yeah, I'm just from the 2D photon echo we're doing here. I mean, we have 15 femtosecond pulses. I would still not be completely confident with things that are 50, 60 femtosecond. I would still be very, let's say, not completely confident. This is very short times, basically. So I don't know if you have any way to deal with this.
So our main form of dealing with these is just making our pulses as short as possible, and then, but other than that, not.
We want to try deconvolution, but I don't think it works too well.
No, I wouldn't expect to.
I have one question to the data. You showed there is rephasing, non-rephasing, and total.
Mm-hmm.
And the total seemed to be also quick, but like independent of the phase or delay between the first two pulses. Because you had there the sum and difference, and then when you sum it up,
Mm-hmm.
you lost this delay between 1 and 2, right?
Yes.
So can you like measure the total spectra like just using 3 pulses? Is that the conclusion?
So we need all of our pulses because we're detecting fluorescence, and so it's the addition of the 2 spectra that gives us our total correlation, not the addition of our pulses. I don't know if I understand your question.
So the phase between 1 and 2 is basically the delay between the first 2 pulses, right?
Mm-hmm.
So
Well, it's
Phase between 1 and 2 is delay between, no. It
no.
is that delay between the 2 pulses probably, that is not the phase difference. It is the wave packet evolution.
So,
So this is
so our phases are, we're modulating the phase of our pulse at like 5 kilohertz and 8 kilohertz. We scan over a time delay, and then we take the Fourier transform of that. And so we're taking out at,
so this is different phase. Okay.
yeah.
Okay. And then my second question, I still didn't get your argument of the uphill transfer. I saw the downhill transfer.
Yes.
So,
Would it be that excited state absorption plays a role in this
yes, I was
context?
thinking the same, that it's the recovery of the excited state absorption.
It's very likely, but I haven't had a chance to analyze it, and so all I can say is that it is favoring it. I don't know why it is.
But can you maybe show it or try to explain it to me once again?
Okay. So, because when we look at our plots, we're seeing the increase of our lower off-diagonal peak and our lower diagonal peak and our upper off-diagonal peak. They are increasing or changing in intensity to a much greater extent than the lower off-diagonal and the upper diagonal. So there is more transfer going on amongst those. So we would expect if there's more change with that, it's favoring that change, then our smaller change is less favored.
And that's what Joachim said. I think that's one should probably think through what could happen with excited state absorption, because okay, all your signal is positive. You don't see explicitly excited state absorption. Somewhere it is, and if it's changing, then and the rest is the same, then you could actually see the effects what you see and think that okay, my stimulated emission or something was changing, but actually that was the excited state absorption, what was eating up or adding or whatever.
Yes.
Yes. Like if I would have this data, I would attribute the upper cross peak to recovery of excited state absorption. And then you still have, have a little bit of growth in the green one.
Well, if there's no excited state absorption, this picture basically tells you that something, your upper peak doesn't go in, but the lower peak, yeah, well, there's no transfer between the diagonal peaks, but you just transfer out to the cross peaks, right? And this makes very little.
Yeah, it doesn't
This
make
makes
sense.
this makes
it
no
doesn't make
sense.
sense that the lower one is growing and the upper one is not decreasing.
You see a grow-in in the upper cross peak, and you don't see a grow-in in the upper diagonal peak. So, I mean, the energy goes to this peak, but it doesn't appear in any state, basically.
One of the problems is that when we have to normalize our data, we have to pick a spot, and so in this case, I think I picked a spot close to our upper diagonal, so it may just be a factor of normalization that we're not seeing much of a change in our upper diagonal peak.
This is an issue if you're going to do some kinetics, no?
I have a more general question. We have two OPAs. You could think of doing two color, tuning them to different values. Not for this sample,
No.
but for something else maybe. Have you been discussing that kind of experiment?
We discussed it, and then instead we have built a non-collinear optical parametric amplifier to get a broader pulse length. And so last week we took the OPAs off the table and put the NOPA down there. So at this point we're not going to do two color, but there is the possibility of it if we were to reconstruct that system. Julia did do a couple experiments with two color, but not very. When she started looking at 6MI samples, there's a very large split in the 6MI, so the OPA pulses weren't able to reach both excitations. So she tried to do two color to be able to look at it, but it wasn't working out well. So we built the NOPA to try and get both of them.
So what is the time frame that Andy has to try some single modular stuff here?
He has talked to me about it, but we haven't started building anything, so we'll see. I know he really wants to do single molecule, but I would like to get a handle on analyzing just the normal data before I try to do single molecule. Yep.
Okay, so there are no more questions. Thank you. Yeah, thanks for all of you for joining this.
Thanks very much.
I wonder if
Three.